Hello everyone, this is Serene from Exam Help Lab. Today I will be solving Chemistry Paper 2 AF Level Structured Questions, May June 2020, 9701 Variant 1. Question number 1. Gallium is a metal in group 13 of the periodic table. Part A. There are two stable isotopes of gallium, gallium-69 and gallium-71. Part 1. State with reference to subatomic particles how the isotopes differ from each other. So an isotope of an element is one which has got different number of neutrons. All right, they have different number of neutrons, but they've got same number of protons. Part 2. State what further information is needed to calculate the relative atomic mass of gallium, since there are two isotopes of gallium existing, so we need their relative abundances in here. To calculate the relative atomic mass of gallium. Part B. Gallium and its compounds show similar properties to aluminium and its compounds. Gallium reacts with excess chlorine to form gallium trichloride. Part 1. At 500 degrees Celsius, gallium trichloride is a gas, suggests the type of attraction that exists at 500 degrees Celsius between atoms within a gallium trichloride molecule. Just like aluminium trichloride, gallium trichloride atoms are covalently bonded to each other. And just like aluminium trichloride molecules are attached to each other through temporary induced dipoles, and so are the gallium trichloride molecules. That's a chemical property of gallium trichloride, and so is and Part 2. When gallium trichloride is cooled, a solid Ga2Cl6 forms, suggests the name of the attraction performed between two gallium trichloride molecules to form Ga2Cl6. That's a dative bonding. Part C. Gallium metal reacts rapidly when exposed to air. A white solid layer is formed on its surface. Part 1 suggests an equation to describe the reaction occurring when gallium metal is exposed to air. So just like aluminium, gallium reacting with oxygen, this gives gallium oxide. We need to balance this equation too, since this question has 2 marks. So each mark goes to the correct equation and balancing. Part 2. The table gives the formula of each gallium-containing product formed when gallium oxide reacts separately with hot aqueous hydrochloric acid and hot aqueous sodium hydroxide. Give the name of the type of behavior shown by gallium oxide in these reactions. So that's amphoteric oxide, since it is reacting with both acid and an alkali. Question number 2, part A. The equation shown in A1 describes the reaction which occurs when aqueous potassium iodide is added to aqueous copper 2 sulfate. A white precipitate of copper 1 iodide forms in a brown solution of iodine and potassium sulfate. Part 1. Balance the equation and include state symbols. So there are 2 CO. I'll balance the equation first and then label the state symbols later. So over here they say that aqueous potassium iodide, this is an aqueous state, is added to aqueous copper 2 sulfate. Similarly over here aqueous. A white precipitate of copper 1 iodide. So a precipitate is in solid form in a brown solution of iodine and potassium sulfate. They're using the word solution means this is an aqueous state. Both of these are gonna be in aqueous states. The table gives the oxidation numbers of iodine in different species in the equation. Part 2, deduce the oxidation number of copper in CuSO4 and CuI. The oxidation number of copper in CuSO4 is plus 2, since SO4 2 minus the polyatomic ion has an overall charge of negative 2, so that it balances the whole thing. Oxidation number of copper in CuI is plus 1, since iodine has an oxidation number of negative 1. Getting to balance the oxidation numbers. Part 3, describe the type of reaction shown by the equation in A, part 1. Explain your answer in terms of electron transfer. So over here, as we can see that Cu over here has got an oxidation number of plus 2, and iodine in potassium iodide has got an oxidation number of negative 1, whereas on the right side of the equation, copper has got an oxidation number of plus 1, whereas iodine over here has got an oxidation number of 0. So I see that Cu has decreased by 1 and iodine has increased by 1. So I'll say that's a redox reaction, and the reasoning to it is that copper gains electron and iodide loses electron. Part B, in the reaction described in A part 1, a student uses 17.43 grams of CuSO4 YH2O. By further titration of the reaction products, the student concludes that the total amount of CuSO4 in the sample is 0.0982 moles. Use the data booklet to complete the table to calculate the value of phi, where y is an integer. Show you're working. First of all, I'll write my equation over here. There were 2 moles of CuSO4 reacting with 4 moles of potassium iodide, which gave 2 moles of copper iodide plus 1 mole of iodine gas plus 2 moles of potassium sulfate. Since in the question mass for SCuSO4.YH2O has been given to us, which is okay, so 17.43 grams of CuSO4, hydrated CuSO4 was used. This means that 17.43 grams contains both copper sulfate plus water molecules. And the next information given to us is number of moles of only copper sulfate, excluding water molecules, and that is 0.0982 number of moles. With this number of moles, we can find the mass of copper sulfate by multiplying moles with molar mass of copper sulfate. So moles into molar mass of copper sulfate. And so mass of copper sulfate being used in this equation is 15.7 grams. And now CuSO4 hydrated has a mass of 17.43 grams, and part of that has a mass 15.7 grams, that is of only, of course, copper sulfate. So mass of water molecules present would be equal to 17.43 minus 15.7, and so it is equal to, and so mass of H2O molecules is equal to 1.76 grams. And then when we divide it with the molar mass of water, that is 18, we get 0.0976 moles of water being used in this equation. Now that we have moles of CuSO4 and that of H2O, we can easily find out the value of Y by taking ratios of both number of moles. I'll write them over here. CuSO4 ratioed with H2O. CuSO4 had 0.0982 number of moles, while H2O had 0.0976 number of moles. When you divide them, you will get a ratio of 1:1, which means that Y has a value of 1. There was only 1 mole of CuSO4 and 1 mole of H2O in the sample, so Y has a value of 1. Question number 3, nitric acid can be made by reacting nitrogen dioxide with water. The enthalpy change for the reaction can be measured indirectly using a Hack cycle. Part A, explain what is meant by the term enthalpy change of formation. So that's an enthalpy change or energy change when 1 mole of product forms from its elements under standard conditions or states. All the enthalpy change definitions, you will need to learn them. Part B, complete the Hash cycle using the values given in the table and hence calculate the enthalpy change for this reaction. Show your working and okay. Since the enthalpy change of formation values have been given to you, you must find enthalpy change of reaction of this reaction with the help of all the enthalpy change of formation values. Enthalpy change of formation is forming 1 mole of products from its elements. So to form nitrogen dioxide, we need oxygen gas and nitrogen gas. Similarly, for water, we need hydrogen and oxygen. Likewise, for nitric acid and nitrogen monoxide to form, we need hydrogen and nitrogen and oxygen. So these are all the elements which will be forming these products: NO2, H2O, HNO3, and NO. Okay, the direct path calculations are given to us, and part of the indirect path to reach our product has also been given to us. So we have to just calculate the rest of the half of indirect path, and that is the enthalpy change of this reaction. Now, enthalpy change of nitrogen monoxide is 91.1 kilojoules per mole, and that for 1 mole of nitric acid is minus 173. But since 2 moles of HNO3 are being produced, so total enthalpy of direct route, which is this one, is negative 254.9 kilojoules per mole. Now coming towards the part of indirect route, enthalpy for 1 mole of nitrogen dioxide is 34. So we'll multiply it with 3 since 3 moles of NO2 were used in the reaction plus 1 mole of H2O. So total enthalpy of part of indirect route, which is this one, is negative 184 kilojoules per mole. The rule is the enthalpy of direct route should be equal to enthalpy of indirect route. Enthalpy of our direct route is negative 254.9, and total enthalpy of our indirect route is negative 184, plus part of it is unknown to us, and that is what we have to calculate, which I'll consider over here as x. So part of that, so x, or part of the indirect route, has a value of negative 70.9 kilojoules per mole. Again, in this question, we used enthalpy change of formation to calculate the enthalpy change of reaction for this equation if we were given with enthalpy change of combustion values. These names over here would have been different. Over here we would have mentioned carbon dioxide and water, but since we were given with enthalpy change of formation values, we mentioned all the elements possible to form these products. To form the product, there is one indirect route always in chemistry, and there is one direct route. Direct route is to forming products right from their elements, and the indirect route is to form something from their elements, and that something will then form the product. So this was a direct route to form nitric acid and nitrogen monoxide right from their elements, and this whole step, these two steps made an indirect route, means elements to nitrogen dioxide and water, and then nitrogen dioxide plus water to form nitric acid and nitrogen monoxide. And this is how you decide which one is your direct route and which one is your indirect route. Part C, nitrogen and oxygen do not react at normal atmospheric temperatures. Explain why. So the only reason for it is that nitrogen has got strong triple bonding, which requires more energy to break those bonds. Nitrogen oxides can be formed naturally in the Earth's atmosphere from nitrogen and oxygen in the air. Part D state one way that nitrogen oxides are produced naturally. So that's through lightning. Part E, nitrogen dioxide acts as a homogeneous catalyst in the oxidation of atmospheric sulfur dioxide. Part 1, explain why nitrogen dioxide is described as a homogeneous catalyst. Since this question has been given 3 marks, so you have to write 3 separate points by explaining what catalyst is, what does it do, and what does homogeneous mean. Okay, so first I'll explain what homogeneous catalysis is all about. Homogeneous catalysts are in the same phase as of reaction mixture. Second point would be about what catalysts are and what role does it play in this reaction. Catalysts would speed up the reaction by lowering the activation energy. And the third point is they remain chemically unchanged. So 3 separate points, each of it will be gaining 1 mark. Part 2, write equations which describe the two reactions occurring when nitrogen dioxide acts as a catalyst in formation of sulfur trioxide from sulfur dioxide. Sulfur dioxide reacting with nitrogen dioxide, giving sulfur trioxide plus nitrogen monoxide. This nitrogen monoxide, actually nitrogen dioxide had to remain chemically unchanged as we described in the earlier part. So nitrogen monoxide will then turn again to nitrogen dioxide. As to keep the statement valid for the catalysts, that they remain chemically unchanged throughout the reaction. Question number 4, calcium nitrate reacts with ammonia, carbon dioxide, and water to form a mixture of ammonium nitrate and calcium carbonate. Part A, explain why ammonia is described as a Bronsted-Lowry base in this reaction. So, ammonia accepts proton because Bronsted-Lowry base explains that a base is a proton acceptor. The product mixture can then be added to soil. Part B, state 2 reasons why this mixture of products is added to some soils. So, first of all, I see that the product has ammonium compound, and ammonium compounds are very useful as fertilizers. Secondly, calcium carbonate used to neutralize the acidic soil. Like if your soil gets too acidic, you can add calcium carbonate to increase the pH of it and make it neutral. Part C, complete the table to name the shape and give the bond angles of each species. So this is all again theory. You have to learn by heart that carbon dioxide has a linear shape and it has a bond angle of 180 degrees. Ammonia has a shape of a pyramid, so a pyramidal shape, and it has a bond angle of 107 degrees. Water is not linear, so it's a bent structure with a bond angle of 104.5 degrees. There is much more to this. You have to learn around 6 or 7. You have to learn all their shapes. You have to learn their bond angles, like for SF6, for methane and all. Question number 5, part A. Below is a list of species which can react with organic compounds. There is a cyanide ion, hydrochloric acid, there is chlorine single atom, water, and then carbonate ion. Part 1 from the list, identify species which can react with ethane. Okay. So with ethane, we can react this chlorine standalone atom, because this chlorine standalone atom actually means that it's a chlorine radical. So with ethane, this chlorine radical can definitely react. Part 2, from the list, identify 2 species which can attack the pi bond in ethene. This is HCl and H2O, because these two would break heterolytically in different reactions. H from both HCl and H2O will be having partial positive charge that will be attracted towards pi bonds, since pi bonds are high in electron density. HCl and H2O would react with pi bonds. Part 3, from the list, identify a species which can be used to distinguish between solutions of propanoic acid and propane 1-O. Describe any relevant observations. So a metal carbonate can be used to differentiate between acid and alcohol. When that metal carbonate is added to alcohol, there is no reaction going to take place. But when it is added to acid, effervescence can be seen due to carbon dioxide forming. So I think it's carbonate ion which can help us differentiate between propane 1-O and propanoic acid. So carbonate ion can be used. Next point would be with propanoic acid, effervescent, but no reaction with propane 1-O. Propane 1-O. Chlorine radical gas can be made from chlorine gas. Part 1, describe the conditions required for this process. So this is I think most of you would remember that this is the initiation step of free radical substitution reaction, where bond between chlorine atom will be breaking homolytically. So for free radical substitution reactions, the first condition is the UV light. And chlorine gas has a bond which is breaking homolytically, so this is a homolytic fission. Each electron being shared between chlorine atoms is now being taken away by both the chlorines, so it's a homolytic fission. Part C, 1, name an organic functional group which reacts with a nucleophile in an addition reaction.
Would somewhat look like this, and when it reacts with HCN, it undergoes nucleophilic addition to form OH over here, and CN from HCN comes here. So I can write that an aldehyde functional group is one which reacts with a nucleophile in an addition reaction. Part 2, name an organic functional group which tends to react with a nucleophile in an SN1 substitution reaction. So SN1 mechanisms have stepwise mechanism, means an intermediate product forms which should be very much stable. So I think of a tertiary carbocation, which looks like this. this is a tertiary carbocation plus a functional group which will be replaced by a nucleophile. So this structure can have a halogen attached to it, like chlorine bromide or chloride bromide or iodide. So answer is a tertiary halogenoalkane. I couldn't think of a tertiary alcohol because there can't be a nucleophilic substitution with tertiary alcohols. It's usually halogenoalkanes. Because for nucleophilic substitution reaction, we need the bond between this carbon atom to break its bond with whatever it is being bonded with over here heterolytically. Means this carbon atom will now be having a partial positive charge, and whatever was bonded to it with this carbon atom would be having a partial negative charge. And so this partial positive charge on this carbon atom will be attracted towards the nucleophile. So for that to happen, we need a tertiary halogenoalkane, because halogenoalkanes, there are way more electronegative than carbon. So this carbon atom will definitely get a partial positive charge, and that halogen will get a negative charge. Part D, but-1-ene reacts with steam in the presence of concentrated phosphoric acid to form two isomers of molecular formula C4H10O. Each reaction occurs via a different intermediate ion. Draw the structure of both intermediate ions. Okay, so but-1-ene is this is but-1-ene. When it reacts with water in the presence of concentrated phosphoric acid, basically an addition reaction is happening, because these conditions like steam and concentrated phosphoric acid, they all are reagents and conditions for addition reaction. So it forms two kind of products. They're both are isomers to each other, which means that if I add steam to it, there's gonna be an addition of hydrogen and a hydroxyl group. So this is either gonna be having an OH attached to it over to this carbon atom, OH being attached to this second carbon atom, because this double bond over here can lead to OH being attached to this carbon atom or this carbon atom. But to circle the more stable intermediate ion drawn in D part 1, explain your answer. So I would say that this is gonna be the more stable one, and the reason to it is that because the circle one forms a secondary carbocation, which is more stable due to greater positive inductive effect of alkyl groups. Question number 6, 2-methyl-but-1-ene reacts with acidified manganate 7 ions under specific conditions to produce two organic compounds X and Y. Okay, so manganate 7 ions, they're an oxidizing that's an oxidizing reagent. X immediately reacts with the acidified manganate 7 ions to form carbon dioxide and water. Y has the structural formula CH3, CH2, CO, CH3, so that's a keton. So first of all, I'll draw the structural formula of 2-methyl-but-1-ene. So it's So 2-methyl-but-1-ene. So 2-methyl-but-1-ene would look like this. Part A, draw the skeletal formula of 2-methyl-but-1-ene. So it's this way. The first one has a double bond, and then this one has a methyl group attached to it. Part B, 1. State the specific conditions required for the acidified manganate 7 ions to react with 2-methyl-but-1-ene in this way. So when 2-methyl-but-1-ene reacts with acidified manganate 7 ions, it forms a keton, and this means that acidified manganate 7 ions need to be hot and concentrated. Part 2, name the type of reaction occurring to the functional group in 2-methyl-but-1-ene in the reaction in B part 1. So that's very much clear. It's oxidation which is taking place. because manganate ion is an oxidizing reagent. Part C, draw the structural formula of X. Okay. Usually what would happen is if there is a structure like this, this when reacts with KMnO4, means hot acidified and concentrated KMnO4, turns to carboxylic acid, where the CH3 or whatever is there remains the same, like here, and CO and OH are the new bonds forming. So over here in this 2-methylbutene, now coming to this carbon atom, which is sharing two of its electrons with these two hydrogen atoms, should have directly formed carbon dioxide. But in this question, it's a stepped one, so the intermediate product would be, which is X, would form an acid. And because it was having a hydrogen attached to it over here to the right, we'll have a hydrogen over here. So X is basically nothing but a methanoic acid, which is basically an intermediate product. It had to be it has to be carbon dioxide, because carbon to carbon double bond on the left, there are two hydrogen atoms on that carbon, so that carbon has to give carbon dioxide when it reacts with acidified potassium manganate. So I'll write HCOOH, methanoic acid. Part D, describe a chemical test and the expected observation to confirm the presence of the carbonyl functional group in Y. For carbonyl compounds, we have 2,4-dinitrophenylhydrazine. If a carbonyl compound is present, that would give an orange precipitate. Part E, the infrared spectrum of 2-methylbutene is shown. Predict two main differences that would be seen between the spectra of Y and of 2-methylbutene. Give reasons for your predictions. Your answers should refer only to the region of each spectrum above 1500 per centimeter. So I'll be ignoring all the peaks before 1500 per centimeter. Considering all the peaks after 1500 centimeter means this one, there will be a strong peak. Strong peak means a broad one, a thick one. Strong peak between 1670 to 1740 per centimeter, due to the carbonyl bond which is present in Y, and a weak peak at 3100 per centimeter, which is over here. This is a weak peak, means this is not that broad, or what, it doesn't have any width. This will not be present in our new spectrum graph, which is due to double bond C, single bond H will disappear. Part F, propanoic acid is reduced by LiAlH4. Part 1, write an equation to show this reaction. Use hydrogen, use the symbol to represent an atom of hydrogen from the reducing agent. So using this, you represent reduction taking place. CH3, CH2, COOH. We add that to hydrogen, and then it gives reduction of carboxylic acid will give you a primary alcohol. So CH3, CH2, CH2OH. Sometimes we have to add water molecule to the right side of the equation in order to balance the equation, in order to balance the number of oxygen atoms. And so I've added H2O over here, and now I'll add a 4 over here. Part 2, name the organic product formed in this reaction. So this is propane 1-ol. Part G, organic compound. W is an ester, which is a structural isomer of propanoic acid. Part 1, state the molecular formula of W. So structural isomer means they share the same number of carbon atoms, they share the same number of hydrogen atoms and oxygen atoms. So propanoic acid has got 3 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. Part 2, draw a possible structure of W. So this means W and propanoic acid both have now C3H6O2. So you have to have an ester with 3 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. So now let's draw a few of the possible structures. The first one we'll be drawing is ethyl methanoid, the first ester formed with 3 carbon atoms. This is the first one which is possible with 3 carbon atoms. So this is ethyl methanoid, which is made after ethanol was added to methanoic acid. Over here it has got 3 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. So this is one of the possibility. Now let's go to the next one. This again has got 6 hydrogen atoms, 3 carbon atoms, and 2 oxygen atoms. We can't proceed with the next ester as we have got only 3 carbon atoms, so you can draw either of these two. Either of them can be ester W. So that's it for this video. Thank you for watching.